one can construct such object to prove the existence called constructive proof, or if not possible, to construct such an object explicitly one can still prove the existence by considering different possibilities or cases. See example below. So this one is called a non-constructive proof. Okay, so let's look at an example. Show that there exists. So this one is example of constructive proof. Show that there exists a positive integer that can be written as the sum of cubes, of positive integers in two different ways. Okay, so this is an example of constructive proof. Constructive means we are looking for an object of interest. In this case, we are looking for an integer that can be written as sum of cube of two positive integers in two different ways. So for example, see 9 is sum of two cubes, 1 cube plus 2 cube. But it's just one way. You want to find an integer that can be written this sum of cube of two integers in at least two different ways. So 9 can be written as 1 cube plus 2 cube, but that's just one way. We need two different ways. So we are looking for such objects. So we can try to construct such object by just checking one by one. But of course, it's hard to do it without a computer, right? But with a computer, you can check, do the calculations much faster. But without computer, you have to do, for example, 9 is 1 plus 8, but cannot be written as another way. Then you can check 10, whether it can be written as sum of two cubes or no, and if yes, is it one way or two ways, right? But with computer, you can check this fast. So one can check with a computer that n equals 1729 can be written as, so 1729 can be written as 10 cube plus 9 cube, and also can be written as 12 cube plus 1 cube. So sum of two cubes in two different ways. One time 10 cube plus 9 cube, another time 12 cube plus 1 cube. So we construct, of course, using a computer, but we still constructed an integer or the object of interest, in this case, integer that can be written as sum of two cubes in two different ways. So that means such an integer exists since we found one, right? So for example, you want to know whether there exists a person who is richer than, or whose, let's say, investments, for example, worth more than $1 billion. But if you find, okay, so this person, you find the person, actual person, the name, last name, you find the person, you say, okay, this person, I found it, I checked his investment, for example, is $2 billion. So if you find the person, that means that the such person exists, right? So we found an integer that has our property. So that means such an integer, of course, exists. Now another, so this is called constructive existence proof. Now example of non-constructive existence proof. Show that there exists irrational numbers x and y such that x to power y is rational. Okay, so here we do not, of course, if we can find an explicit example of irrational number x and irrational number y such that x to power y is rational, well, that would be great. You know, it's just, again, a constructive example. And again, constructive example means the object of interest, of course, exists. But it's hard to construct such example explicitly. And therefore, we want to prove the existence not by constructing an explicit case. Let's see how. So solution. Consider the number root 2 to power root 2. It's one irrational number raised to another irrational number, and raised to an irrational number. Both irrational numbers, of course, are the same, but irrational number raised to irrational number. Now this number, root 2 to power root 2, is it rational or is it irrational? Well, you can try to see whether you can find out whether it's rational or irrational. But right now we want to show whether it's rational or irrational, even without trying to find out which one, which case is. We can still show the existence of the object of interest here. How? By considering cases. Remember, we said in non-constructive case, we can still prove the existence by considering cases or possibilities. I have a number √2 to power √2. There are only two possibilities. Either this number is rational or irrational. In either case, I'm going to show the existence of the object of interest, which is in this case an irrational raised to irrational number and becomes a rational number. So case one or possibility one, if √2 to power √2, this number is rational, then set x equals √2 and y equals √2, and then x to power y is rational as desired. Okay, we were looking for irrational numbers x and y, where x to power y is rational, where in possibility one, if √2 to power √2 is rational, x and y both set both of them to be √2, then x to power y becomes rational, and that's it. Now case two, if √2 to power √2 is irrational, then set x equals this number √2 to power √2 and y equals √2, then x and y are irrational, right? Because in case two, in possibility two, I'm assuming that √2 to power √2 is irrational. Therefore, I'm allowed to set x to be this number. Remember, my x and y are supposed to be irrational, and x to power y has to be rational. Well, if this number is irrational, I'm allowed to set x to be this number. Y, I can set it to be √2. Then both x and y are irrational. And x to power y will be how much? √2 to power √2, then the whole to power √2. How much is this number if I simplify? √2 to power √2 times √2 is 2. √2 to power 2 is 2, which is rational. So x to power y is rational. So whether this number is irrational or rational, in either case, we could show that there exist numbers x and y, irrational numbers x and y, with x to power y being rational. Okay, so even without being able to construct it explicitly, we could still prove the existence. Okay, now then we also want to look at the uniqueness. So uniqueness problems. Once we prove existence of an object of interest, one can prove the uniqueness by assuming there are two such objects, let's say x1 and x2, and proving x1 equals x2. Okay, so like I said, uniqueness and existence, both of them are important in mathematics. Of course, for uniqueness, first we need existence. But once you prove the existence, then the question raises whether uniqueness also holds or not. For example, we said a person whose investments worth more than $1 billion. So let's say I know that person X has investment worth $2 billion. But then uniqueness, the question of uniqueness raises. Is that the only person whose investment worth more than $1 billion, or there's another person in the world whose investment worth more than $1 billion? So in mathematics, once we prove the existence, we can show the uniqueness by assuming there are two such objects, let's say x1 and x2, and prove that x1 has to be equal to x2. And then that means that the uniqueness must hold. So let's look at an example. So example, show that if a and b are real numbers, and a is not equal to 0, then there is a unique real number R such that AR plus B equals 0. Okay, so first for existence, we want to prove the uniqueness, but first we need the existence. So proof first existence. And we know that for existence, we can do constructive or non-constructive. For simple examples, usually we can do constructive. So what can you construct a number R such that AR plus B is equal to 0? Well, that's very easy, right? Just a simple equation. AR will be minus B. Therefore, R has to be, so constructive, R has to be minus B over A. So set R equals minus B over A. Then AR plus B will be A times minus B over A plus B, which will be 0. And uniqueness. For uniqueness, we said, okay, we can assume that there are two such objects. You can call it x1 and x2, or in this case, because R is used, so let's call them R1 and R2, and then show that R1 has to be equal to R2. So suppose there are two numbers R1 and R2 such that AR1 plus B equals 0 and AR2 plus B equals 0. Then what can I conclude? Then I can say that AR1 plus B has to be equal to AR2 plus B. And then if I subtract with B, I can say AR1 equals AR2 and divide by A, because A is not equal to 0, right? So I can divide by A, and then I can say R1 has to be equal to R2. Okay, another maybe more non-trivial example, division algorithm. Division algorithm. So suppose B is bigger than 0, then for every integer A, there exists unique numbers Q and R called the quotient and the remainder such that A is equal to QB plus R and R is bigger than equal to 0, less than B. So assume existence of Q and R prove the uniqueness. Because we want to work on uniqueness here. So of course, existence has to be proved as well. So i.e. skip the proof for existence, right? So when I say assume, I mean skip the proof. Of course, the existence has to be proved, but let's see how we can prove the uniqueness, because we want to give an example of how one can show the uniqueness of an object in mathematics. So this is about division algorithm. We can always divide A by a positive number B, called divisor, right? And then there's always a quotient and a remainder. And the remainder is always bigger than or equal to 0, less than B. And quotient Q has the feature that A is equal to QB plus R. So for example, let's say if A is, for example, 12, B is 5, then 12 is equal to 5 times 2 plus 2, right? So this is your B, this is your Q, quotient is 2, and remainder is 2 as well. And 2, I can say is bigger than or equal to 0, less than B, 5, right? So remainder has to be bigger than or equal to 0, less than B. And in this case, 2 is less than 5, as we expect. So this is just a simple example, simple elementary school example of division algorithm. So division algorithm has to be proved. The proof has two parts: existence of remainder and quotient, and uniqueness of remainder and quotient. Right now, we want to prove the uniqueness. So proof. So how do we said, how can we prove uniqueness in mathematics? We can assume that there are two such objects. Right now, there are two types of objects of interest: the quotient, which we call it Q, and the remainder, which we call it R. So suppose there exists Q1 and Q2 and R1 and R2 such that A is equal to BQ1 plus R1 and also BQ2 plus R2. Okay, because our A has to have the property that is equal to QB plus R. Now, if there are two such Q and two such R, let's say Q1, Q2, R1, R2, then A has to be BQ1 plus R1 and also BQ2 plus R2 at the same time. And what is my goal? Our goal is to show Q1 equals Q2 and R1 equals R2. Okay, now so how can I do this? So see, we have BQ1 plus R1 equals BQ2 plus R2, right? Because both of them are equal to A. So if I take BQ2 to that side, BQ1 minus BQ2 equals R2 minus R1. And then that means B times Q1 minus Q2 equals R2 minus R1. Now, let's take absolute value B times absolute value Q1 minus Q2 equals absolute value R2 minus R1. And B is, remember, positive by assumption. So B times absolute value Q1 minus Q2 equals absolute value R2 minus R1. Now, if, remember, I want to show that Q1 is equal to Q2 and R1 equals R2. Now, if Q1 is not equal to Q2, right? Then the left-hand side, Q1 and Q2, of course, are integers. If you have two distinct integers, the difference will be non-zero integer. Absolute value of non-zero integer will be at least 1, right? We also saw in another example today. Absolute value of a non-zero integer is at least 1. Integers means what? Means 0, 1, 2, 3, minus 1, minus 2, minus 3. If it's non-zero, means either 1, 2, 3, minus 1, minus 2, minus 2, minus 2, minus 3. So in absolute value, you have a number which is at least 1. Right? So if Q1 not equal to Q2, then Q1 minus Q2 will be not equal to 0. And therefore, absolute value Q1 minus Q2 will be bigger than equal to 1. Therefore, B times the left-hand side of, so let me call this one star. Left-hand side of star will be bigger than equal to B. What about the right-hand side? Right-hand side, what do I know about the right-hand side? I know that R1 is bigger than equal to 0 less than B, R2 bigger than equal to 0 less than B. So what can I say about R1 minus R2? So what can I say about minus R2? Minus R2 will be bigger than minus B less than equal to 0, right? So let's add it with, I just multiply with minus 1, it flipped the inequality. So if I add these two, R1 minus R2 will be bigger than minus B less than B. So I have a number which is bigger than minus B less than B. From pre-calculus, that it means that the absolute value of this number has to be less than B. So that means absolute value R1 minus R2 less than B. Because if X is between minus C to C, then absolute value X is less than C from pre-calculus. So that means right-hand side of star is less than B. Left-hand side was bigger than equal to B, right-hand side will be less than B. So I will have a contradiction if Q1 is not equal to Q2. I want to show Q1 is equal to Q2, but if Q1 is not equal to Q2, then I have a contradiction. Why? Because then left-hand side will be bigger than equal to B. Left-hand side of an equation, this equation is will be bigger than equal to B. Right-hand side is less than B. So that's a contradiction. So this contradiction, this is contradiction with left-hand side bigger than equal to B. This contradiction shows that Q1 is equal to Q2. Q1 is equal to Q2, what implies what? So what did we have? We have, remember, we have BQ1 here. BQ1 plus R1 equals BQ2 plus R2, right? So let me write it again. BQ1 plus R1 equals BQ2 plus R2. But I just showed that Q1 is equal to Q2. So that means BQ1 plus R1 equals BQ1 plus R1. So this cancels with this. BQ1 plus R2. This BQ1 cancels from both sides, and I'll get R1 equals R2. So I showed that Q1 equals Q2 and R1 equals R2, which proves the uniqueness. Okay. There's also another, so next topic, another method of proof, backward proofs. So in mathematics, and specifically improving inequalities, we sometimes prove the inequality. Let's say we sometimes prove by starting with the goal and simplify until we get a statement that we know it is true, and then we check that the steps are reversible. This method is called backward proof. Okay, so let's look at an example. Let x bigger than 0 show that x plus 1 over x is bigger than or equal to 2. This is a very interesting inequality in mathematics that says a number plus its reciprocal is always bigger than or equal to 2. You can think about some simple examples. For example, 5, as long as, of course, the number is positive. 5 plus 1 over 5, of course, bigger than 2. Even if the number is less than 1, for example, 1/2. 1/2 plus 1 over 1/2 is 1/2 plus 2, which is also bigger than or equal to 2. If the number is 1, 1 plus 1 is bigger than or equal to 2. So any number plus its reciprocal, as long as the number is positive, is bigger than or equal to 2. So let's see how we can prove this inequality. So backward proof, we want to use backward proof. In backward proof, what do we do? Like we said, we start with what we want to show. Sometimes we prove by starting with the goal and simplify until we get a statement that we know is true, and then check that the steps are reversible. So we start with what we want to show. What do we want to show? We want to show this inequality. X plus 1 over x bigger than or equal to 2. Then I want to simplify this using the properties of inequalities. I can simplify this. How can I simplify this? Well, I can, first of all, I can get common denominator. So that means x squared plus 1 over x, right? The common denominator is x, bigger than or equal to 2. Then I can multiply both sides by x because x is positive by assumption, right? Remember, we saw in another example today that if you have an inequality, you can multiply both sides of the inequality with a positive number and the inequality remains the same. If you multiply with a negative number, inequality will flip. So then I'll get x squared plus 1 bigger than or equal to 2x. And then that means x squared minus 2x plus 1 bigger than or equal to 0. And that means x minus 1 the whole squared bigger than or equal to 0. So I reached to, so remember, I started with what I want, with my goal, what I want to show, and I reached to a statement that I already know it's true. I know that x minus 1 the whole squared is, x minus 1 the whole squared bigger than or equal to 0 is true, right? Because why? Because any number squared is always non-negative, right? So this is, we know this true, it holds, let me say, since any number raised to power 2 is non-negative. Okay, so I start with the goal and I reached a statement that I already know is true. But I didn't want to show that x minus, I wanted to show x plus 1 over x bigger than or equal to 2, not x minus 1 squared bigger than or equal to 0. I already know that x minus 1 squared bigger than or equal to 0, right? So now I have to reverse the steps, because I am allowed to basically start with what I want. I am allowed to start with what I know it's true, which is x minus 1 squared being non-negative. So basically I have to start with this and then conclude this, then conclude this, then conclude this, and then conclude this one that I want to show. But I did the opposite. I started with my goal and I reached something that I know it's true, right? But the logical procedure is to do the opposite. Start with what I know is true, then conclude this, then conclude this, then conclude this. So that's why I'm saying that in this step, after you reach a statement that you know it's true, then you have to check the steps are reversible. Because what we need logically is the opposite direction, starting with this, then going to this, going to this, going to this, right? So after you reach this step, you can write down that since the steps above are reversible, we can conclude that x plus 1 over x bigger than or equal to 2 for x bigger than 0. Why are the steps are reversible? Well, that's very easy to check. If you want to start with this and then reverse it to this one, well, that's obvious, right? Well, this one we know it's true, any number squared is non-negative. And then from this, we can easily conclude this. Why? Well, because x minus 1, the whole squared is x squared minus 2x plus 1. And then from this one, we can easily conclude this one. Why? Well, I can just take, this 2x to the other side. And that's it. And then from this one, we can conclude this one. Why? We can divide by x. Because x is positive, the inequality remains the same. So from this direction to this direction, we multiplied by x. But if you want to reverse this step, we have to divide by x. But in any case, we are allowed to do that. We are allowed to multiply with a positive number, also divide by a positive number. So from this direction to this direction is also from this step to this step. The conclusion also holds. And then from this step to this step, again, it's obvious because x squared plus 1 over x is same as x plus 1 over x. So every step is reversible. Right? So that means the inequality we want to show is true. So let's look at one more example for this topic. Show that example, let a and b be positive numbers. Show that a plus b over 2 is bigger than root ab. So this is called arithmetic mean of a and b, and this is called geometric mean. Of a and b. So this question basically want to show that once we have two positive numbers, the arithmetic mean is always bigger than geometric mean. How can we do it? We want to do it with backward proof. Backward proof. What do we do in backward proof? We start with the goal. So the goal is a plus b over 2 bigger than root ab. And then we simplify until we get to something that we know it's true. We know it holds. And then we check that the steps are reversible. So let's do that. So I start with this. Then what can I conclude? I can multiply both sides by 2, of course. Then I can say a plus b bigger than 2 root ab. And then I can take everything to one side. So a minus 2 roots ab plus b bigger than 0. Now I can write this one as root a squared, right? Minus 2 times root a, root b, and b can be written as root b squared. So this one, in this step, the only thing I did, I replaced a with root a the whole squared, b with root b the whole squared, and root ab is root a times root b. Because remember, a and b are both positive. So of course, root ab is same as root a times root b. Now I have an identity, x squared minus 2xy plus y squared. What is it? X minus y the whole squared. So root a minus root b the whole squared bigger than 0. So why is this true? So this one holds. I reached to a step that I already know it's true. I already know it holds. So this holds. This inequality holds. So here, let's also assume that a and b are positive and not equal to each other. So let a and b positive with and a not equal to b, and we want to show this. So this inequality holds since let's say x equals, if I set x equals root a minus root b not equal to 0, because a is not equal to b, right? So I have to add the assumption that a is not equal to b, because if a is equal to b, then this number here could become 0, and 0 squared is not bigger than 0. It's just bigger than equal to 0. But because the inequality, I want it to be strict. So this number in the left-hand side has to be non-zero, and it will be non-zero if root a and root b are not equal, meaning that if a and b are not equal. So that's why I added the assumption a not equal to b, so that this inequality holds. So this inequality holds since x equals this not equal to 0. And therefore, x squared is bigger than 0, right? So we know that x squared is positive if x is not 0. X squared is always bigger than or equal to 0 for every real number x. But if I know that x is not 0, then I can say x squared is strictly positive. So please remember this. It could be a little bit confusing. I repeat one more time. X squared is bigger than or equal to 0 for every real number x. But when can I say that x squared is strictly bigger than 0? If x is any real number but 0, except 0. So here, x is root a minus root b. I set x to be root a minus root b is not 0, because by assumption a is not equal to b, and therefore x squared is bigger than 0. So this step is true. So I started with my goal. I reached a step that I already know it's true. I wrote here why it's true. And what is left to do? So at the end of your proof, you can add since the steps above are reversible, we can conclude that a plus b over 2 is bigger than root ab as desired. So why are they reversible? Again, it's very easy to check. From this step to this step, you want to go backward, right? So that's why it's called backward proof. From this step to this step is very easy. Just use the identity x minus y the whole squared, x squared minus 2xy plus y squared. And then from this step to this step, well, root a the whole squared is of course a, root b the whole squared is b, root a root b is root ab. And then from this step to this step, again, it's very easy. You just need to take this term to the right-hand side. And from this step to this step, what should we do? We have to just simply divide by 2. And then we get this statement, which is what we wanted to prove. Okay, guys, so these are some examples of backward proofs. So I will include more examples of each method of proof in exercises. And of course, but in the exam, normally it's not written that which method you have to use. So you have to do lots of practice in order to be comfortable with different methods and in order to be able to recognize which method of proof is the best to use for each given question. Okay, guys, so I'll upload the assignments and see you soon next time.